So today I want to tell you about security bounds for succinct arguments from hash functions. So it will be mathy, hopefully understandable. So we all know about succinct arguments. Just to remind you, they are cryptographic proofs, right? For computation integrity, so we want to prove the correctness of executed computations. They have this very wonderful special properties, efficiency properties. They're super short and super fast to verify. They have their origins in the 1990s, and they were born at the intersection of two areas of theoretical computer science, computational complexity and cryptography. And for the in the past 15 years, there's been extraordinary progress in many aspects of these wonderful objects at the cryptographic foundations, efficient constructions, implementations, and applications. All right. So where do they come from? Succinct arguments are typically constructed according to various recipes. You may be familiar with some of them. For instance, you can combine a linear PCP and a linear encoding, a PCP with a hash function, or a polynomial PCP with something called a polynomial commitment. Doesn't matter. These are just some names of some recipes. They all have a shared template. There is somehow, somewhere, a type of probabilistic proof and some type of cryptographic commitment. And together, they come to form a succinct argument. These two ingredients, they bring different things to the succinct argument. Usually, the probabilistic proof contributes the type of computation that you might be proving, for example, a circuit or a machine. Whereas the cryptographic component, the cryptographic commitment, determines other qualitative features of the succinct argument, such as which cryptographic costs you're going to have in the prover and in the verifier. Is it a pre-quantum or post-quantum construction? Do you have a setup, and what type? Today, I want to focus on security. Okay, so you have these two ingredients coming together, the probabilistic proof and the commitment. How is the security of the resulting succinct argument depend on the security of these two ingredients? Now, this question is going to be different for each recipe. So today, I'm going to focus on the particular case of PCPs, and we'll see IOPs, plus hash functions, because this is the one that is most relevant for the technology used in StarkWare. Okay, so that's the plan for today. I want to tell you about that. All right. Also, I forgot to say I have 30 minutes, including questions, so you can stop me with questions along the way. So please raise your hand and just ask. And if there's too many questions, I'll continue. But do feel free to stop me along the way. All right. All right. So about probabilistic proofs, the way I like to picture the different types of probabilistic proofs is by first clarifying what are the kind of different powers that are granted to the verifier. You can think about these are the kind of four basic different types of powers you can grant to the verifier. Do you have one or more provers? Are you allowed to interact with the prover? Does the verifier have randomness to use? What kind of access do you have to the messages, the oracle access, right? And depending upon which power you grant to the verifier, you get different types of probabilistic proofs. So among the most basic, there is an interactive proof that combines the power of interaction and randomness. A PCP combines the power of randomness and oracle access to the proof. An IOP, the type used in StarkWare, combines simultaneously interaction, randomness, and oracle access. And then you have other types of proof systems, such as a multi-proof interactive proof, or even something that encompasses all of them. And an oracle access further factors into different types of access to the proof. Is it like a point query, or do you have a polynomial query, a linear query? So this gives you different types of access to the proof. And these different probabilistic proofs have qualitative features. Interactive proofs primarily serve as subroutines to other types of probabilistic proofs, because on their own, they're not very powerful. PCPs are fantastic from a pedagogic perspective, but we don't have efficient constructions for them, so they're not really used. Multi-proof interactive proofs have fantastic features such as space efficiency, but they're very hard to use because we don't have great cryptographic commitments to pair them with. Yes? I am blocking part of the slide, that is true. So I'll stay over here. Thank you. Good question. Comment. IOPs are the ones that are kind of most popular and most used because they're very efficient, and today they underlie most modern succinct arguments. So this is kind of the high-level view of probabilistic proofs without getting much into details. So I said today we'll talk about probabilistic proofs, specifically PCPs and IOPs, plus hash functions. So let me say a little bit about hash functions. A cryptographic hash function has a certain output size, lambda, that is the security parameter. And it's an algorithm that maps an arbitrary length input to this lambda bit output. And the kind of intention or the desiderata is for this function to have no useful structure. And kind of, to make a long story short, often in practice, you model these hash functions as just random functions. Okay, to every input, there is like a random output, the end. That's like a random function. This leads to the notion of random oracles, random functions. And in the random oracle model, every party, honest or malicious, has query access to a randomly sampled function f, okay, with a certain output size. And so now we want to start talking about security a bit more concretely. And so you can think about stating security in this model as theorems that have this type of template. You have some adversary A that gets to query the random oracle some number of times, t. That's a parameter, okay? That's like the number of times, the size of the adversary, you can think about it, like how efficient your adversary is going to be. And then you want to quantify the probability that the adversary with these t queries is going to break your scheme. For example, a cryptographic proof. And so you have some error that is going to be a function of the output size of the random oracle and the power of the adversary, which is the number of queries it makes to the oracle, okay? And so when you want to understand the security of succinct arguments in the random oracle model, what you want to do is you want to understand what is this error as a function of those two basic parameters. And you want that error to be small, or at least understand it, okay? Okay, so these are kind of preliminaries. Let me make sure I'm still on time. Great. Any questions so far? Good. All right, so really, as I said, in practice, we use hash functions and IOPs. But before I get there, it will be very useful to first talk about something that is pedagogically useful but not very efficient, and that is hash functions from PCPs, with PCPs. So constructing succinct arguments from PCPs, all right? So just to remind you, the diagram of a probabilistically checkable proof, it is a proof system where the verifier can use randomness and can make queries to one message from the prover. So pictorially it would be something like this. The PCP has some instance and witness, outputs a PCP string. It's like some long encoding of your computation. You can think about it. And the verifier makes a small number of queries to it and gets back answers. This is a PCP, all right? Important to realize is that PCP is not a succinct argument, because if you just were to ask an adversary, hey, here are my queries, what are the answers? They can always convince the verifier. You have to first write down the PCP, then query it. You cannot let the PCP depend on the queries, all right? Okay, so that is a PCP. Why is it interesting from the perspective of succinct argument? Because there are PCP constructions where the number of queries is, say, constant, regardless of the computation size, and the verifier runs exponentially faster than the original computation. So you want to kind of leverage this kind of speed up in verification over execution. The problem is that you have this long PCP string that the question is, where do you put it? You cannot send it to the verifier, because by that point, the verifier could have just run the computation itself, right? Nor you can just ask the prover to answer a few queries, because they're going to cheat specifically on those queries. You have to first fix the PCP, all right? So in some sense, this is an idealized world where the verifier has magical power of oracle access. And this is where cryptography comes in. Cryptography will let us implement oracle access using commitment schemes, okay? So this leads to the first succinct argument designed by Joe Killian in the 90s, and so it's known as Killians Protocol. And the idea is you're going to use a Merkle tree to commit to the PCP string, and after committing to the PCP string, you're going to reveal just the queried locations that you care about. So intuitively, you have two new entities, the argument prover and the argument verifier. And at least, pictorially, the argument prover is going to run as a subroutine the PCP prover, produce this long PCP string, commit to it using the Merkle tree to produce a short commitment to the long PCP, the Merkle root, RT, send it over to the verifier, and now the verifier says, look, I have a commitment now. The prover has committed to something. Now it's safe to send the randomness for the PCP verifier. Then the argument prover will locally simulate the PCP verifier, figure out what are the small number of queried locations, assemble the answers, and then produce a Merkle proof authenticating those answers. So, the collection of authentication paths for each of the queried locations. And then we'll ship off the answers and the authentication paths. Then the argument verifier will say, okay, let me check that you really did reveal answers that are consistent with the committed root earlier, and then check that indeed when you run the PCP verifier with this kind of partial PCP, and that randomness, the verifier accepts. Okay? So this is a canonical construction, probably the simplest construction of succinct argument that we know, and it's very intuitive. Okay? Any questions about this? All right. So what I want to tell you about now is, let's analyze this one and talk about the security. Okay? So these are the parameters of the PCP up there, the soundness of the PCP, and then kind of the alphabet, the proof length, the number of queries. The nice thing about this construction is that you barely touch the PCP prover and PCP verifier, because the argument prover and verifier up top are just basically saying run the PCP prover and verifier plus some cheap hash functions. So you didn't really mess up any of the efficiency properties of the PCP. You basically preserve them. The communication is succinct because you're essentially paying for query complexity rather than proof length, right? Because you're just sending a root, the answers and authentication paths, that's roughly the number of queries times log the proof length. Okay, so it's much better than sending the original PCP. This is where you gained. And security, kind of the main point of today's talk, is this is the main theorem you can prove. If you have a t-query adversary, so an adversary that can query the random oracle up to t times, the probability that it will break Killians Protocol is the soundness of the PCP plus something like that looks like the kind of birthday bound, okay, t squared over 2 to the lambda. Okay, it's roughly the error of kind of collisions. Okay, this is not obvious. One can prove it. But what's the point? The point is that knowing this, now you can set parameters. So for example, let's say that you were to set the PCP soundness to be a fourth and the output of your random oracle to be 258 bits. What that's going to happen then is that this is going to be 1/4, and that's going to be t squared over 2 to the 258. So if you have an adversary that makes at most 2 to the 128 queries, that will mean that the probability of breaking Killian is at most a half. And of course, if you want to make this smaller, one way would be to just make this and this. Make this smaller and that bigger, right? Okay, the point being is that here, both the PCP and the hash function contributed to the security of the resulting succinct argument. And to make sure that succinct argument is secure, you have to understand this specific relationship and set parameters accordingly. Okay? All right, I'm omitting small constants, but this is the behavior. Great, so we understand the security of the simplest succinct argument out there. All right? Questions? Yes? So the intuition is that when you commit to a message using a Merkle tree, breaking a Merkle tree will cost you something like birthday bound, okay? Because it's enough to cause collisions to kind of create mess in the construction. All right. So, for instance, if you were to commit to 2 different PCPs with the same root, then it would be difficult to conduct a security analysis. I'm not saying that it's necessary, but I'm saying it suffices to rule out collisions in the Merkle tree. Okay. Yeah.
Can you explain what is epsilon PCP, the soundness?
What is epsilon? Yes. Sorry. The soundness of the PCP is the probability over the choice of randomness of the PCP verifier of making the wrong decision. So you kind of fix a PCP for some false statement, and it's an arbitrarily chosen PCP, and you look at the maximum probability of convincing the verifier on that false statement. Okay, so that's like the soundness of the PCP over the choice of the PCP verifier.
I don't understand how you can set this probability.
Of course, if the PCP is given to you, it's just epsilon PCP. But since we construct PCPs, then in the construction, you can just tune it so that it has the value that you want. This happens in practice with, for example, IOPs. You might do more repetitions of the query phase, or you might increase your field size. So you make sure that if you want a certain parameter, then you kind of design your system to be such.
Why not setting it to 0?
That would be wonderful. We don't have such PCPs. Yeah. That would be wonderful. Yeah. And unfortunately, and one can prove that some error is necessary, and then because you don't want just a small error, you want like efficient prover, small number of queries, kind of balancing all these parameters together creates trade-offs, and then then you have to and you have to think hard to design good constructions. All right, check on time. Good questions. More about this one?
Yeah.
Hmm? Yeah.
You said you can design it and tweak it. So in the example of StarkWare, for instance.
Yeah, in the example of StarkWare, like the key kind of soundness contributor is the low degree test, Fry. Okay, and Fry is kind of mostly influenced by the size of the field that you work over. Okay, and the number of repetitions of the queries at the end of the protocol. Okay, so if you want to reduce, for example, the soundness error of Fry, you might repeat the query phase more. That will cause more queries, but it will make the soundness error go down, right? Or you might also increase the field size if it's not big enough.
And what is the order of magnitude of this parameter for StarkWare?
Well, I cannot answer yet because this is not the protocol StarkWare uses, right? So we'll see. This is an interactive protocol, but in the next slide, we'll see something that is closer to what StarkWare uses because it's a non-interactive protocol. And we'll see that the expression changes slightly, and you have to pick parameters differently. So let's go there. So Killian is an interactive protocol, but in blockchains, what you like to do is to write down proofs on the blockchain, so they have to be non-interactive. So what do you do? The idea is that you're going to use the random oracle to do something else beyond the Merkle tree. You will also use it to derive the PCP randomness itself. Okay, this is, for cryptographers, can be understood as applying the Fiat-Shamir transformation to the Killian protocol. Okay? So pictorially, it would be something like this. The argument prover starts out the same way by committing to the PCP. But then, rather than sending the root, you take the root and you stick it in the oracle. Okay? And out comes some randomness. And you say, okay, I'll just use this randomness for the verifier. Okay? And you proceed the same way, using that randomness derived from the oracle. And then you set the proof to be basically the two messages you had before, the root and the kind of answers and authentication paths that came out from the verifier executing on the randomness derived from the oracle. Okay? So this is a non-interactive proof you send over. So this highlighted part in orange is the only difference in the honest prover from Killian's protocol. In the verifier, you rederive randomness the same way, so that at least we're talking about the same randomness. And then you do the same things as before. You check the Merkle proof, and you check that the verifier accepted. Okay? Now, any questions about this? It's very intuitive construction. It's very kind of pedagogically pleasant. It has pictures. Yeah.
What do you mean by you do the same randomness as before?
The same so it's important that the prover and verifier talk about the same randomness, right? So if the prover is supposed to derive randomness, let's say on these two inputs, the root that it sends and the instance they're making a statement about, then the verifier has to do the same. Okay? Now it's important that you derive the randomness based on the PCP. Otherwise, if you didn't, and you were to just say derive randomness from input 0, you could just derive randomness from input 0, see the randomness, and then craft your PCP based on the randomness. So this kind of take the PCP, compress it, and stick it in the oracle creates some sort of chronological order in the head of the prover, and kind of simulates the presence of the verifier as an interactive party without really being there. But it's just intuition, because as we now see, the security changes slightly, okay? So the time efficiency in communication are pretty much like before, but security is very different. And the main reason is that an adversary, when it tries to attack the proof system, in its head can try different PCPs that lead to different roots, that lead to different randomnesses. Whereas in an interaction, it had only one shot. When it sent the root, that's it. It gets one choice of randomness from the verifier. Now, in its head, the prover can try different things and try different randomnesses. Okay? This leads to a slightly different security bound where you still have the collision error here, but now the PCP gets a T in front, which intuitively represents the fact that the adversary can attack the PCP T times, okay, by trying, say, T different PCPs. All right? So this means that even if you just wanted to make the argument have kind of any attack to succeed with probability at most half, your PCP has to be much more secure. Before we had 1/4, but now because we have this T in front, it has to be 2 to the minus 128 over 4, right? I.e. 2 to the minus 130, right? And this is the key difference in sort of when you have non-interactive arguments versus interactive arguments. And so coming back to StarkWare that uses non-interactive arguments based on PCPs, it means that Fry has to be kind of actually secure enough to withstand this team front. Again, I'm not talking about IOPs yet. This is the PCP, but that's the analogy, okay? All right. All right. Now, this would be great and fine. The only problem is that we don't have PCPs that are practical, so the construction that I described is not really used in practice, okay? But otherwise, it's a great kind of pedagogical warm-up, all right? Questions? Yeah?
What do you mean by they're not practical?
I mean that they are sorry?
Is epsilon not small enough?
Asymptotically, they have great behavior. It's just when you look at the constants, it's like, yeah, like it's not very useful in practice. They're not absolutely terrible. Actually, a long time ago, with Eli, when I was much younger, we tried to kind of make PCPs. It was before we had the idea of thinking about IOPs. We tried to make PCPs, as practical and efficient as we could, but kind of we made progress from making them never halt to halt on small, very useless programs. But then it's just very rigid object, and there's not many. Yeah, the state of the art is still not quite practical. Yeah. The constants are big. Yeah.
I have a question. Why is the amount of queries the adversary makes relevant to performance? Is the lower bound to context?
Yeah, you can think about this parameter t as a lower bound on the size of the adversary. Of course, a real-world adversary would have to kind of marshal all these invocations of the hash function. Even running the hash function itself might take a few cycles within the processor, right? But surely, like if it takes this number of invocations of the hash function, then your adversary will run at least that much. Another caveat, though, is that this analysis is modeling the hash function as an ideal hash function. Real hash functions are not ideal because they're efficient. That's a different story. Okay. Yeah. All right. All right, got 7 more minutes. I want to talk a little bit about IOPs. All right. So in practice, succinct arguments are built from IOPs, not PCPs. Okay. And so these are proof systems where not only you have randomness and oracle access, but you also have interaction. So the way it looks is something like this. The prover and verifier exchange messages. The verifier sends randomness. The prover sends some oracle, receives randomness, another oracle, and so on and so forth. And at the end, the verifier makes some number of queries to potentially each of the oracles. All right? And fortunately, known IOPs are vastly more efficient than known PCPs. Okay? It doesn't mean that it's like a necessity. It's just the current state of knowledge today is such. And we can, fortunately, construct succinct arguments, including non-interactive ones, from this more general interactive object. And IOPs essentially kind of underlie all modern succinct arguments. So how do you compile these objects, and what is their security? So we can try to do something like before and say, okay, first let's talk about an interactive argument. And we can just proceed by analogy. We just saw an interactive protocol for PCPs and a non-interactive protocol for PCPs. And we can say, look, an IOP is just a multi-round PCP. So if I wanted an interactive succinct arguments, I could just apply the Merkle tree for each of the IOP strings. Killians Protocol was just on one oracle. Now we have more, but what's the big deal? Let's just do it for each oracle. And the main idea to achieve to remove interaction was to use the oracle to derive randomness, rather than having the verifier to stick around and chat. And we're going to do the same here. It's a little bit more complicated, but that's the same idea, okay? So in the last 5 minutes, I'll just show you the pictures of these protocols and talk about the security, okay, how it's kind of changes, all right? And this is what is used in StarkWare, up to kind of engineering, important engineering optimizations. All right, so let's first talk about interactive case. I have some IOP, and I want to turn it into an interactive succinct argument. So I have the IOP prover. It produces some oracle. I commit to it right away with a Merkle tree. I send over the root to the verifier. The verifier receives it and says, OK, I'm ready to sample the first randomness to send to the prover. receives it, produces the next PCP, and so on and so forth, until you go to the last PCP, last IOP string. You do a Merkle tree on top of that as well. You receive the final randomness, and now the argument prover can simulate locally the IOP verifier. And I think part of the slide is chipped at the bottom, but what it no, here it is. It will send over all of the answers for each of the oracles authenticated relative to the respective Merkle root, right? So there's going to be one collection of authentication paths per Merkle root, all right? So it's just repetition of that earlier paradigm. And you check that all these proofs are correct, and then the IOP verifier runs, accepts given these partial strings, right? So like before, all of these hash functions on top don't really change much the efficiency of the underlying IOP prover and IOP verifier, okay? And like before, the communication is roughly query complexity. The security also is, one can prove, is pretty much like in Killian's protocol. You're going to have the soundness error of the IOP plus the collision error. Okay, it's completely analogous to the case of Killian. So one can prove it, and I'm not going to prove it here, and it works. All right. Now let's get to the, yes? It's a good question. The question is there no difference whether the prover sends all the answers in the end versus along the way? So right now I'm talking about so-called public coin IOPs, which means that the verifier sends only randomness. And for such public coin IOPs, one can assume without loss of generality that all the queries are at the end. So in such a case, they're all at the end. A different story is whether it's not public coin and then more complicated things happen. And you can ask me after the talk what happens there. Up to very small constants, yes, it's the same probability. Why would you use this one? Because we have practical IOPs, but we do not have practical PCPs. We would absolutely use the previous protocol, we just PCPs are not efficient enough. But IOPs are efficient enough. Yeah.
You asked a slightly different question on if you send over the Merkle roots after each query, or if all the Merkle roots arrive at the end. Is that
No, the Merkle roots have to be interleaved with the randomness. Otherwise, you're not preserving kind of the interaction, right? So that's important. All right, so I have the last 2 minutes for what actually happens in practice. So we don't, okay, if you're fine with a succinct interactive argument, that's a fine construction. But in many settings, you want things to be non-interactive, okay? So what you're going to do is, again, by analogy, you're going to apply the Fiat-Shamir transformation to this prior protocol. That's roughly how it looks. You kind of behave like before, but when you take the root, rather than sending it, you stick into the oracle, and you get the randomness there. And the next time around, you take the root, you are going to stick it into the oracle, but it's important that you preserve chronological order of the different rounds, and you take the previous output, and you stick it also in the next oracle together, okay, to keep things in order. This is a common paradigm used in blockchains. That's a hash chain to keep things in order, right? This is also known as the Fiat-Shamir transformation. And so you do this as long as you want for however many rounds. Eventually, you get back kind of all the randomnesses. You can simulate the IOP verifier, and you send everything as a non-interactive proof. The verifier rederives the randomness in the same way, and then, like before, it checks all the Merkle tree proofs and runs the IOP verifier. I guess kind of the crux of this talk comes now. Can I have 1 minute? Yeah, okay, I'm allowed to have 1 minute. Efficiency is the same, but security is vastly different. Like before, an adversary could kind of try different choices of randomnesses in its mind by tweaking the PCPs, thereby changing the Merkle roots. It can do it here too. And it's as if the adversary were to conduct an attack against the original IOP by trying different transcripts. Here's an execution, and it says, yeah, I don't like this execution. I'll try a completely different one. And it says, you know what? I'm going to try to change the second one to fork, kind of start from the same transcript as this one, and then try a different continuation. Okay? So it can do this, let's say, t times. Okay? Exploring different transcripts, different continuations. And this is known as a state restoration attack. All right? So it's you can basically reduce any attack against the compiled protocol to an attack of this sort against the underlying IOP. And the slightly kind of tricky thing that happens is that, the first thing is that you can prove that the security of that protocol, what is used in practice, is characterized by this state restoration soundness error, okay? It's like the success probability of such attacks. The sad news is that in general, such soundness can be much worse than the normal soundness, like exponentially worse in a number of rounds. But fortunately, IOPs that we construct, they don't have this worst case behavior. It just kind of gets degraded linearly, like in the case of a PCP. So in this case, essentially, you have essentially the same security as the Micali construction, and you got efficiency for free. Even though you were using this many-round protocols, and in principle, a many-round protocol causes state restoration attacks to be very successful, for protocols that we care about, that doesn't really happen. They're very special. They have something called round-by-round soundness, where these ugly things just don't happen. And so in practice, you have to set parameters of the underlying IOP to take into account of that linear factor, like in the PCP construction. Okay, I think I'm going to stop here because I got to the point of saying this is how the security bound of practical succinct arguments works. And yeah, I'll stop here.